Right. So today is going to be much more relaxed than last time, even more relaxed than last time. We'll be talking about flows in graphs, or on graphs. And my terminology and notation is just a wee bit non-standard. So let me go through the notation carefully in case you've seen flows before, which I hope you have not. But the main thing to start with is that we have a multigraph whose edges are not not directed. So we don't have a directed graph. We have an ordinary undirected multigraph. And so we can have parallel edges and we can have loops. And every edge has two directions. So if we have an edge E between two vertices x and y, maybe there are more than one, then this has two orientations, as I call them, orientations. So we write down E just to specify that we're talking about this edge, not those two. And then which way we oriented. So this is from x to y, and this would be the same edge from y to x. Okay? So we have undirected edges with orientations. That's important. And now to introduce flows, we just take an abelian group H, and I'll write this additively as usual. Now, normally this will not be some high-flying complicated group. It's just going to be the integers, or maybe the integers mod k, and maybe some simple Cartesian product like z2 times z3. I'll write the integers mod k as z index k. And then we'll have values from this group H on the oriented edges or on the orientations of our undirected edges. And so if we have a set of vertices x and maybe its complement y, then an f is a map from the orientations of our undirected edges to our group H, an abelian group, then f of x comma y is going to be the sum. Oops, that wasn't a good sigma. That wasn't a good sigma either. That's better. So it's going to be the sum of the f values of edges between x and between a vertex in x and another vertex in y, oriented from the x vertex to the y vertex. So for every such edge, take the value under this function of the orientation of that edge from x to y. And the sum of all these things is going to be f of xy. Now, this is the simple way to envisage it. But I will allow x and y to intersect. So if x and y have a large intersection, maybe it's quite okay to consider edges that have one vertex, the first vertex in x, and the other one in y, but still also in x. That's completely okay. then we take the f value of such an edge into this sum f of xy as well. And similarly, if we have both vertices in the intersection, right? And even for loops, if the first vertex of the loop is in x, and the other vertex, also the first, is in y, then like here, where this vertex is in the intersection, then this would be an xy loop, but it does not count for f of xy. So loop values are ignored. That's important to realize, or to remember. Okay? So f of xy, this one, is the sum over all edges between distinct vertices of their f values of the orientation from the vertex in x to the vertex in y. Right. So now what are flows? They come in two variants. There's a more general notion, which I call circulations, and then there's a more restricted version, which I call flows, always maps from the orientations of edges to our group. And the flows will simply be certain circulations, namely those that don't assign 0 to any oriented edge. Okay, so what are the two requirements for such a function to be called a circulation? There are two. F1 is that the f values on the two different orientations of the same edge must be inverses of each other in this group. Okay? So if this is 2, then this is minus 2, or the other way around, when h is, for example, the integers. So that's F1. The intuition behind that is to say, well, if the value of this oriented edge is 2, then we can think of flow, a certain amount of flow with value 2, not very much flow, but a little bit, going from here to there, and we can think of that as minus that amount flowing the other way. Okay? And the other requirement is F2. F2 simply says that when we have a vertex, little v, and we sum over all the incident edges to anywhere, so f of v comma big V, that's the entire vertex set of our graph, then this has to be 0. That's the requirement F2, right? All the flows out of a vertex sum to 0. Therefore, all the flows into a vertex also sum to 0. That's the inverse in the group, the negative. And there's a neat way of rephrasing that. If you partition the edges at V in any old way you like, so for example, like this, 3 edges here and 3 edges there, if the first edges are now, if you orient them inwards towards V, and think of their values as flow going into V, then that must be the same as the sum of the values of the other edges, the flow that leaves V. So in equals out in any old way in which you define in or out. So this is not the only partition for which you can do that. You can do that for any partition. And if you reverse the orientations of some of the edges, then that will invert their f value in the group. And since previously the sum of these plus the sum of that was 0, now if you invert some of them, then that will equal that. So that's a neat way of remembering F2. Either you say the total flow out of a vertex or into a vertex is always 0, or you say the amount of flow that goes into a vertex must be exactly the amount of flow that comes out of the vertex, however you define in and out. People that define flows on directed graphs have a problem here. They also state F2 in terms of whichever directed edges go into V, their values must sum to whatever the sum of the values of edges directed out of V is, but the directions are fixed. So here we're much more variable, much more flexible, and that's a good thing. Right, and now that's a circulation. So a circulation is such a map that satisfies F1 and F2, and if it's nowhere 0, as we say, so if it doesn't assign the 0 from our group H to any oriented edge at all, then we call it an H flow, not only an H circulation, but an H flow. Right? So even though we didn't count the value of a loop under F in this definition of F of xy, they do get values. That's important, right? So loops get values under F, and right. So they're exempt from this and this. Well, they're exempt from everything, but they do get values. All right? You can think of a loop, an oriented loop of having its unique value going out of the vertex and then also coming into the vertex. So if you take the sum of this little bit, this edge and that edge, you're summing over the same edge, and you'll be arriving at 0, whatever the value of that edge is. So that's a way of sort of incorporating this into F2, but you don't have to. But F1 just doesn't require anything for loops. Right? Okay. The circulations on a graph form a group. Right? Easy. You have one circulation little f, you have another circulation little g, and you can take the sum of f and g by just summing their values. The sum function f plus g is a well-defined function, and that will satisfy f1 and f2 if little f and little g did. So they form a group, but the flows do not, because you can have two non-zero values summing to 0. Okay, so suddenly when you take the sum of two perfectly acceptable non-zero circulations, i.e. flows, the sum of those two, you get another circulation, but you may find that it assigns 0 to some edges. We're going to be interested in flows, but we'll be working with circulations because they're so much easier to work with. We don't have to worry about leaving the group, or we have a group in the first place of circulations, and that will make life a lot easier. But our ultimate goal at the end of the day is going to be to study flows, not just arbitrary circulations. Okay, and here are a few observations. One is that if we have a circulation, then the flow across any bipartition of the vertex set is going to be 0. You can do a pedestrian proof of that by induction, right? You start with one vertex on the left, and then F2 tells you that the flow out is going to be 0. And then you move one vertex after the other from right to left and proceed by induction. That's the obvious but somewhat pedestrian proof. But another way to view it is to say that f of x and x bar is the complement, you can write that as somewhat artificially as f of x v minus those that you have too many, those that you didn't want. And which are those? Well, those are those from x to x, right? So the edges from x to the complement are the edges from x to anywhere minus those that don't go to the complement, right? So that's easy. Now, this is going to be 0 because it's the sum over all the little x's of f of little x comma v, by definition of this expression here. And that's f2. Right? For a little x, f of little x comma all of v is 0 by this. And this is 0 by f1 because you're summing over all the orientations of edges, and every edge gets considered in this sum once in each of the two directions. And they're negatives of each other by f1, and therefore they cancel out, so they're both 0. So that sums to 0, and that's what we wanted to prove. And a neat corollary of that is that if your graph has an H flow, a flow with values in the group H, then it can't have a bridge. Right? Because the bridge is one edge that forms a cut, one edge across some such bipartition of the vertex set. And if you're an H flow, you're not allowed to assign that 0, but it must be 0 by this. So you have a contradiction. Graphs with an H flow cannot have a bridge. Okay. And now comes another little observation. That's a new lemma. Which is going to be important twice in this group of lectures when we do induction proofs. And this lemma tells you that when you contract an edge E, maybe let's call it E naught. You contract an edge E naught, then any flow on the contracted graph or let's say any circulation, let's address the topic of whether it's going to be a flow or not later. So any circulation on G contracted E naught to a new vertex v e naught. Any circulation on that extends, I'll tell you what I mean by that in a moment, to a circulation on G, always with values in our group H. Now, let me prove that to you. We're assuming we have a circulation on the contracted graph where this little v e naught is one vertex. Now that satisfies F2. So the sum of a collection of edges at this contracted vertex oriented into that vertex, the sum of its f values equals the sum of the f values of all the remaining edges at that contracted vertex oriented out. So f of all these equals f of all those. Okay, so we want to define a circulation on G, and by extend, I mean that, well, all the edges already have f values, except for this edge e naught. That's why I wrote extend. All right, so we want to assign a value to the two orientations of e naught, but that's easy. We have to satisfy f2 at x, and we have to satisfy x2 at y. So the f value in this extended f for all of G, the f value of e naught oriented from x to y has to be the sum of the f values of these incoming edges. And that's a little worrying because we now defined it, and without regard to what happens here. So here, the value of the f value of e naught oriented into y has to be the sum of those. But it is, because the sum of those, as we observed earlier, equals the sum of these here, which we took as the definition of f of e naught oriented that way. Okay, so it seems done, and there's even a unique extension, except I glossed over a little bit, which I now still have to repair. And what's the little bit? Has anyone noticed? Yeah? Yes. So there could be parallel edges here. They're going to be loops at the contracted vertex, but never mind, they're going to have f values, right? And now I have to, now the word extend isn't really appropriate anymore. Now I have to define f values, or f prime values if you like, on the orientations of these edges in G. Now they have two orientations. Formerly as loops they had only one. So we want to use the values that they have in f, but we have to make up our mind whether we use it for this direction or for the inverse direction. So let me decree, and here I'm making a choice, that we always use the existing value under f of the loop at the contracted vertex for the orientation of that edge in G from x to y. Now I have defined f, or if you like, f prime, on all the oriented edges of G, except we have to revisit the definition of f prime on e naught. Why? Well, because all these parallel edges now have values as well. So So they go into this equation here. The inverses of its values contribute to the sum of all edges at x oriented into it, and that has to equal the f value of E naught oriented out of x. So we choose that rather than for f prime of E naught from x to y, rather than the sum just of those f values here. So once more, f prime of E naught oriented from x to y is going to be the sum of all the f values of these edges minus the sum of all the f values of these edges, which we know because they were loops in the contracted graph and had f values there. Okay, and then we have to obviously satisfy f1, so the inverses are going to be the negatives of those, and in the same way as earlier, you can notice that if f2 worked out at this vertex, is also going to work out at that vertex. Same proof as before. So we're done. Questions? No. So let me address the topic of flows versus circulations. If little f wasn't only a circulation, just a circulation on the contracted graph, but in fact a flow, then all the f values were non-zero, including those on loops, by definition of flow. However, it can happen that the sum of all these minus the sum of all those f values, those on the loops, is zero. Right? Why can that happen? Well, easy. These f values are something, and on loops you can specify any f values that you like. You're always going to meet the requirements f1 and f2. So you can easily get to zero. And then the unique, after specifying f prime on these edges and on the edges parallel to E naught, the value on E naught is going to be uniquely determined, namely as the value that I showed you earlier, sum of this minus sum of that. That may be zero. So it's just not true that a flow extends to a flow. A flow extends to a circulation. That is going to be non-zero everywhere except on the edge that we uncontracted, the edge E naught. And what happens there, we don't know. Okay. Questions? No. Right, so here comes our first theorem. And that is interesting because it answers in rather an unexpected way the existence question of, given a group H, given a graph G, is there an H flow on G? And the answer, as the theorem shows, doesn't depend on the actual choice of the group given the graph. It just depends on the order of the group. So that's a rather surprising thing. And the reason is this theorem that says that there exists a polynomial that specifies the number of H flows on a given graph G. And that's a polynomial in the number of non-zero elements of the group, right, on order group -1. Polynomial in that and that is going to be the same for every group of that order. Right? So in particular, as a corollary, if there exists an H-flow for one group and you have another group of the same order, then there's also going to be an H-flow of that group. And we'll prove that by induction on order of G, maybe, number of edges of G. So which shall we choose? Induction proofs, we have to make the graph a little smaller, use the assumption on the smaller graph, and get it back for the original graph. So if we delete a vertex, we find an H-flow on the smaller graph. Can we extend that to an H-flow of G? Here's our one vertex. Here's the rest. We have an H-flow on here. Now somehow we need flow values on these edges. They have to sum to 0 if oriented towards that vertex. So we have a little bit of leeway to play with which edge to give which value so that the sum is 0. But we also have conditions to meet. At the other ends of these edges, we have to satisfy F2 as well. And if we assign anything non-zero to a single edge going out of a vertex here, then F2 that happened to be, that was valid before is going to be invalid afterwards. If we have two edges to the same vertex, maybe we're in better shape, but why should we? Okay? So deleting a vertex doesn't seem like such a good idea. How about deleting an edge? Okay, so we delete an edge. We get an H-flow on the rest. Does that extend to G? Yes, of course it does. The value of this edge is going to be determined and has to be 0. Right? So that's a recipe for disaster. Not only can it go wrong, it will go wrong. So deleting an edge seems to be utterly useless. Okay, contracting an edge. Here we go. Contracting an edge, well, that looks a bit more promising. Except that we have this caveat that maybe we have to assign E0 0, even if we start with an H-flow on the contracted graph. So that's also not going to work. It's going to fail, even though not as dramatically as deleting an edge does. And now comes a brilliant idea. How do you combine two disasters to a working proof? Well, you have all these circulations here, some of which work and some of which don't. Which ones don't work? Those that assign 0 to this edge. But those are precisely the useless ones. Right? Those are precisely the flows on G minus that edge. So if we subtract from the near disaster the total disaster for that edge, we get exactly what we want. Okay, so let me do this a little more formally. We'll be doing induction on the number of edges. Okay? Now the induction has to start somewhere, and we don't start it at a particular number of edges, but in one sweep we prove it for all graphs that have only one vertex, no matter how many edges. All right? And that's easy. So if we have only one vertex and lots of loops, doesn't matter how many loops. So m loops, say, then how many flows are there? How many maps that assign a non-zero group element to each of these edges? Well, all of them, right? So there's for x equals the order of the group minus 1, so the permitted values of our flow, the polynomial in that value in order of the group minus 1, call that x, that counts the number of flows is x to the m, all the maps from m to the permitted values. Okay, so that was easy. And now we write the intended flows that we want as the half disastrous flows minus the total disaster flows. So F1 is going to be the circulations, those are the total disasters, circulations on G with, so let me call them F with F of E naught 0. And technically I ought to put arrows on the E naught, but both of them are 0, right? So those are the real disasters. And F of E non-zero for all other E. And F2 are going to be the circulations on G that are possibly 0 on E naught, but not necessarily. F of E non-zero for all E except possibly E naught, and then E naught backwards as well, of course. Right, so that's the set of all circulations that are non-zero everywhere or everywhere without, except E naught. Both are permitted. Right. So F is these minus those. Right? And also, F1 is a subset of F2. Those that are always 0 on E naught are among those that are maybe 0 on E naught. Right, so by induction we know that there's a polynomial counting this. There's also a polynomial counting that. So the number of these things is going to be the first polynomial minus the second polynomial. Right? I need this here to get from the set difference to the numerical difference. That's it. Right, just notice that this corollary that if H and H prime, two abelian groups have the same order, then either a given graph has an H flow and an H prime flow, or neither. This corollary is not so easy to prove directly, right? So if you have these group values on the graph under H, you can't just take a bijection to H prime and import those values to get a flow, an H prime flow, because they add up differently at the vertices. Right, the addition will be different in H prime, so even if you do the transfer in such a way as to make F1 true, F2 is likely to fail, right? So that corollary is non-trivial, but really easy, and the whole proof was easy. Okay, so next topic, we had flows with values in an abelian group. When the group is the integers, then some of those Z flows get a special name, namely, if k is a fixed integer, then all the Z flows whose values are strictly bigger than minus k and strictly smaller than k, and of course non-zero because they're flows, are going to be k flows, right? Little k flows. So what's a k flow? A k flow is a Z flow with values in a particular range. Namely, the absolute value of a value under this flow must be smaller than k. And of course bigger than 0, because 0 is not allowed in flows. Okay, so that's a k flow. And the flow number of a graph is the smallest k, such that this graph has a k flow. It's not totally trivial to see that this is even defined, that there exists a k for which the given graph has an integer flow at all. Well, because if it does, it will be a k flow for k big enough. K bigger than all the values you used. That's an easy exercise. But if existence is ensured, then the minimum makes sense. So if we say the flow number of G is the minimum of all the k's for which it has a k flow, that makes sense because it's harder to have a k flow for smaller k, simply because you're not allowed to use as many values in your map. So the flow number of a graph is the smallest k, such that this graph has a k flow. Okay. So let's have another. Relation, and that is between k flows and zk flows. So if we have a k flow, so from the oriented edges or orientations of edges, same thing, we have a map to the integers. So an oriented edge gets mapped to some integer little I. Then we can append that by the canonical homomorphism to the integers modulo k for some given k. And my notation for that will simply be little I bar when it's clear which group we live in. So that's going to be the coset I plus zk. All right? So from a k flow, we get a zk flow simply by composition with the canonical homomorphism. F1 and F2 are going to be preserved, in this map, right, negatives in Z map to negatives in ZK, and if something sums to 0, then the images under the homomorphism will also sum to 0. So F1 and F2 are going to be preserved. And the interesting thing is that the inverse implication is also true, that if you have a ZK flow, you can also find a K flow. And that's non-trivial. And before I prove that to you, let's just indicate why we're interested in both. So K flows, just integer flows with a certain value range, are more flexible when we have these for different K, because we can just add them. I can add a 5 flow and a 7 flow, and what I get is another 7 flow, right? Because a 5 flow is a 7 flow, right? The integers that are between -7 and between -5 and 5 strictly are also between -7 and 7 strictly, right? So we can add K flows for different K, yes?
What if the single edge is in some value over 5 plus 7?
Sorry?
What if the single edge in both flows is a value for flows such that the sum goes over 7?
I didn't hear the latter part.
So how do you define addition if not?
In Z. In Z.
Yeah, but why?
The values are always integers, just integers. And we just notice that, I see. So you're asking whether the sum is going to be a 7 flow. Did I say that?
Yes.
Yeah, sorry, of course that's nonsense. It's going to be a 24 flow, or whatever you like.
5
Right.
plus 7.
Yeah, 5 plus 7 is less than 24, so it's going to be a 24 flow. Right? Yes, of course. But it's going to be some K flow again. And you can't add elements of ZK, of Z5 to elements of Z7. They're not going to be elements of Z24. Right? So you can't combine ZK flows for different K as easily. But then for fixed K, ZK flows are easier to handle than K flows because they form a group. Right? And the K flows don't form a group. Right. Precisely for that reason. Right. So if you add a 7 flow to another 7 flow. Okay, so how should we prove this? We were given a ZK flow little g, and we want a K flow F on the same graph. Right? So the idea, of course, is to undo this. Right? So we should want a K flow such that if we compose that with the canonical homomorphism, then we'll get precisely our G. Right? So we want F such that sigma K performed after F is our G, where this is this homomorphism here. Right? And now, we have little g to start with. So for example, if k equals 5, we have a value of, I don't know, 3 bar. And we could turn that into 3, because if we have 3 and we apply the homomorphism, we get 3 bar. But we could also send it to -2, right, which is the same modulo 5. So that would also work. And we don't know which is better. But it will make a difference, because our f will have to satisfy f1 and f2. And, okay, we could probably say, okay, if we give it 3 in one direction, so in the other direction, then we give it -3. So we fix it only in one direction, and then let the other direction be completed automatically so as to satisfy f1. And if we chose -2 here, then we would choose 2 there. So f1 is easy to keep happy, but f2 is not easy to keep happy. So the proof will construct from the given g an f that satisfies this, in some iterative process, which I'm going to describe to you now, where at the start we're generous and we allow it to violate f2, but at the end we want f2 to be satisfied at every vertex. We'll be changing, improving that candidate for f in steps. Okay, plenty of time. Okay, so here are the conditions that we impose on our attempted definitions of little f. So let me write them down explicitly once more so that I can refer to them later. Condition 1 is that we want f1 to hold, but not necessarily f2. We're generous concerning f2. Second is we want sigma k composed with f to be the g that we started with, the zk flow. Then we want the values to be in the correct range. So f of some oriented edge little e should be have an absolute value strictly between 0 and k. And now we have another requirement, namely we compute the penalty for violating F2. And we call that K of F. And that's the sum over all vertices little x of f of x big V, and the absolute value of that. Right? So these things ought to be 0. These things. If we have f2, then this is going to be 0. Then the absolute values are going to be 0, and then the sum is going to be 0. So when we have arrived, k of f will be 0. And if k of f is 0, then we have arrived, because this ensures that it's a k-flow, it's a map to the integers, and f1 holds. Fine. So let's try to take an arbitrary f that satisfies 1 to 3 and change it so as to improve 4. Okay, is the strategy clear? Yeah. So just a question. If I deleted these bars here, if we summed over the values themselves rather than their absolute values, do you know what the sum would be? Multiple of something, yes, true. It's going to be 0. This is going to be 0 because this sum without the absolute value bars, so let me write it again to avoid confusion. The sum little x over v of f of little x comma big V, what's that? That's simply f of VV, right? So that's 0. And because that is so, we can learn from the assumption that we have a positive defect here, penalty. We can learn from that there must exist a little x where this is going to be negative. F of x v is negative. And we have another one, let me call it x prime, where f of x prime v is positive. Why? That's because all the f's, all these things, sum to 0, but they're not all 0. So if things that are not all 0 sum to 0, then some are negative and others are positive. All right, so there exists one that, where this is negative, and there exists one where this is positive. And the idea now is to travel from one to the other by some path where ideally f is positive on all the edges. Let me just see if I have it the right way around. No, I have it the wrong way around. So just to make it consistent with the write-up that you have. So at x, we have more out than is allowed, and here we have more in that is allowed. So it's conceivable that there's certainly going to be an edge out of x where the f value is bigger than 0. Maybe we can get a little closer to x prime along another edge where the f value is positive. And if we can travel all the way to x prime, well, that's like in the max flow min-cut theorem that you have seen in graph theory 1. Then we just pick the minimum of all these excess values and send that amount of flow back. Or we take the minimum of these values and subtract that from f, in which case this is going to be closer to 0. That is also going to be closer to 0. And we shall have improved k of f. That's the idea. Okay, so how can we find this path? Well, as in the maximum min-cut theorem, let's just see how far we get. Call big X the set of all vertices to which you can get from little x on an edge whose f value is bigger than 0. We'll be happy if little x prime is in that set, but maybe not. And we shouldn't get too hung up about this little x prime that we found earlier. If we can find another little x prime with this condition somewhere in here, then that'll be just as well. In fact, better, right? So we would like to be able to travel from x to some xy with this condition on edges on which f is positive in the direction of travel. Okay, so just for technical reasons, let me define the set x prime as x minus little x. So we want little x prime to lie in big X prime. Right, so let me show you that some little x prime can be found in big X prime. And that you see here. Whoops. Right. So the sum over all the elements of big X prime of these values, which for the little x prime that we're looking for, we would like to be smaller than 0, want to be negative. So we're going to find such a little x prime by summing over all of them and showing that the sum over all of them is negative. Then there must exist at least one where this value is negative. Right? So let's sum over all of them, and then there will exist one where this is negative if the sum is negative. So this is simply f of big X prime v. Right? We're summing over all the elements of little x prime. So that's this. What's that? That's all the edges with first vertex in x prime and the other vertex anywhere, and we'll just write that as a more instructive sum. So that's x prime to the outside world, those across the divide here, right? Those are the edges from x prime to those vertices that aren't even in x, plus f of big X prime to little x, right? Little x is also not an x prime. So out from x prime goes out of x or to little x. And in this sum, of course, we also have those edges that stay inside x prime, right? But this is 0. This is also 0, or let me say at most 0. Why? By definition of x prime. X prime was all the edges that you can get to from little x on the path whose f value is positive on the edges along that path in the direction of travel. So any edges out of x prime, not back to x, but further on, do not put that other end vertex in x prime, because why not? Because the edge from the x prime vertex to that outside vertex, here for example, the value of this is not bigger than 0, otherwise this would be an x prime. So this is at most 0. And so likewise, all these are at most 0. So this is at most 0. But this one here is less than 0, right? By definition of x and x prime. So all the edges out of little x to other vertices in x prime have positive f value. So the other way around, from the other edge of other vertex in big X prime back to x has value less than 0. Okay, so this sum here is strictly less than 0. That means there must exist a little x prime, not anywhere, which we know already, but in our big X prime, where this is also less than 0, which is our condition here. So this little x prime does exist inside big X prime. Oh, we don't need it up there anymore. Okay, so back to our plan. We now wanted to send some flow back from X prime to little x. And let's call that flow little h, right? So we add little h to f. I want to show that f plus little h satisfies 1 to 3 again. 1 to 3. Well, in order for f plus h to satisfy 1, it's enough that little h satisfies condition f1, because f does and then the sum of those two will also satisfy F1. In order for F plus H to satisfy this, well, adding H to F should not change its value under the canonical homomorphism. What does that tell us? You can remember your answer that you gave earlier. Right. So the value under little h has to be a multiple of k to leave this invariant, right? We want the sum to be the composition to be G again. So the values of under little h are all multiples of k. Okay. More precisely, we want little 3 to be valid as well. So, well, if f had its values strictly between minus k and k, then little h shouldn't catapult that out of the permitted range, right? It should still be between, so we have 0 here, minus k here, and k there. If we add 5k, if the value under h is 5k, and the value under f was in this permitted range, then after that it's going to be outside that range. So the only possible values under little h are going to be k and minus k, right? So if the f value was somewhere here, then f minus k is there, which is still permitted, and the other way around. So little h must have values between either minus k or k. Yeah. Well, we don't want it to be 0 because we want to improve big K of f. We want to send, that was the argument I gave you earlier, so we want a positive values on these edges, which we then deduct. So, sorry, since I wrote f plus h, we want negative values, not 0 values, negative values on these edges, and it should be the same value of h along all these edges, because we don't want to upset whatever we had achieved for f2 at these vertices in between. So if h is minus k on this edge, it must be minus k on that edge as well, and minus k on that edge as well.
So we only define h on those edges?
Yes. Right, we're allowed to do that because we're in the business of improving our performance of f2 at x and minus x while leaving it untouched at other vertices. And so we can define little h on the edges only of this path. But additive inverses of each other for the opposite directions, of course, so as to satisfy f1 for f plus h, multiples of k to satisfy this for f plus h, and h being not any multiples but minus k or k to satisfy this. Okay. So does this, in fact, reduce big K of f? Well, there's a little caveat. If we have a value close to 0, and then we subtract k, then we get something in the permitted range, but whose distance from 0 is bigger than it was before. So we have to be a little careful. However, we only want to improve the sum over these, not on individual edges, but on the sum of all the edges out of X. So in order for this is positive, then we have H in this direction with value minus k added to F. And on this direction too, and this direction too is always minus k. Then how does that affect not just this little edge? That might be dangerous, but the sum of all these values here. Well, same problem. If the value of this sum here over all the edges out of little x is bigger 0, but only just, then taking k away from it might increase its absolute value and make our bound, our penalty worse. So in order for this to actually go down, we need that this sum is actually bigger than half k. Right, so if this sum is here, then taking k away from it brings it closer to 0 in the absolute value. Well, is it? What are these values here, which we want to be bigger than half k? We know it's positive. Is it also bigger than half k? That's right, your standard answer. Sorry? Precisely. It's 0 mod k because G was a circulation and it's bigger than k, so it must be at least k. Brilliant. So done. Okay? Right, that's it.